Hello, we meet again on iPad. So we're going to continue the discussion of power series that we started from the last recording. So we have a power series of the form, which is an expansion. It's a series expansion about a point A, and we discussed that there is a radius of convergence. So here is the point A, and there is this interval upon which the series will converge, and we call that this is called interval of convergence. So every point that lies within this would converge, and we also have this radius of convergence, namely that, let's pick a different color. If we pick this interval for capital R, then this is R is called radius of convergence. And the summation for the series usually goes from 0 to infinity, and this would converges for every x that you pick that is lying within this interval of convergence. And because it is meaningful for every x within this interval, so it becomes a function of x, and so we can write it as f of x. On the other hand, when we are looking at the boundary, so that is this point and the other point, the right hand point and the left hand point, we don't know what they are, whether the function will be meaningful or not. So if that's the case, we need to look at them separately. So today we want to talk about manipulation of power series. Alright, so the simplest example to start with would be to consider this geometric series of 1 over 1 minus x, which can be written as the sum of x to the power n goes from 0 to infinity. So when expanded out, you can write it in this form, and this is valid provided you restrict x between minus 1 and 1, which means the interval of convergence is between minus 1 to 1, and the radius of convergence is equal to 1. Now let's look at a slightly different example of 1 over 1 plus x squared. Does it have a power series expansion? The answer is yes, if you do a slight surgery by making a right substitution. Let's say we put 1 over 1 minus capital X, where capital X is equal to little x squared minus x squared. So if that's the case, I can get a geometric series expansion provided I restrict my capital X. And we just copy from the last line, so this would give me capital X to the power n goes from 0 to infinity, so this would be reduced to 1 plus capital X plus capital X squared plus capital X to the power 3, and continue provided we have restrict capital X to be less than, strictly less than 1. In other words, as far as capital X is concerned, it's just a power series with radius of convergence equals to 1, center at capital X equal to 0. So now we can revert back to little x. So we have little x, remember this is square, raised to the power n, and goes from 0 to infinity. So the right hand side would becomes 1 minus x squared plus x to the power 4 minus x to the power 6, and continue until you have minus x squared to the power n, and continue. And provided capital X, in this case, is equal to minus x squared. But after you take the modular sign, so this is simply more x squared, and you want that to be less than 1. And so as far as this relation is concerned, it makes very little difference. When x squared less than 1 is the same as x less than 1. So the restriction is still the same. And we have the interval of convergence to be minus 1 to 1, and the radius convergence is equal to 1. So we do have a power series expansion for this 1/1 plus x squared, which becomes like this, provided we make this restriction in line with the restriction for the power series, geometric series. Okay, so let's look at a few more examples. So here's another one. So suppose you have 1 plus x plus 2. So the idea is try to make it into the form that is familiar to us, like the geometric series. So in this case, we want to think of it as 1/2, and then you have 1 plus x divided by 2 in this form. And then you can think of this as simply 1/2 times 1/1 plus capital X, where capital X is this time equal to little x divided by 2. To be more precise, you can think of it as let me do a slight change. So because the geometric series we always minus, so we put a minus sign in here, and then we put a minus sign there. Okay, so now you see that we can continue the computation to be 1/2. So then this will simply becomes capital X to the power n goes from 0 to infinity. And now we're going to substitute. Of course, here, if for this expansion to work, you need to restrict more capital X less than 1. Nevertheless, under this assumption, I can now plug in the little x, which is replaced by this form. And so after simplification, this would be the sum of minus 1 to the power n x to the power n, and divided by 2 to the power n goes from 0 to infinity. And since capital X corresponds to little x divided by 2, so if you restrict this to be less than 1, then this is equivalent to saying that you restrict x is less than 2, small x less than 2. Okay, so continuing the computation, we can now plug in, multiply the factor of 1/2 into this. So to simplify, since we have a 1/2 down here, so we would get n goes from 0 to infinity of minus 1 to the power n x to the power n divided by 2 to the power n plus 1. And this is going to converge provided you have more x less than 2. And in other words, the interval of convergence is going to be between minus 2 to 2, and the radius of convergence is going to be equal to 1. So that's the situation that, for this example. And other than that, if we continue the discussion, we'll see that, so this is actually a theorem, which I quickly point out. If we're going back to this set of notes, as you can see, so this is the last section of this note. So what it says is that if you have a function defined by a power series like this, with certain radius of convergence, then you can actually differentiate the power series with the same interval of convergence. So maybe I put it more clearly. So same interval and radius of convergence. Then you can actually differentiate the term one by one, and you go from 0 to infinity. And so this is going to give you n of x minus a to the power n minus 1, and this time n becomes 1 to infinity. And it will still be converged as a new power series converging in the same interval, same radius of convergence. And furthermore, you can integrate. So in this case, you would get the integral like this, 0 to infinity, and you can actually swap the two and you integrate 0 to infinity, and this would give you the sum of an of x minus a to the power n plus 1 divided by n plus 1. N goes from 0 to infinity in this form, plus a constant. And still for the same interval and hence radius of convergence. So this is quite amazing. So there are three parts. So we assume f has this particular expansion. Then we have both the derivative and the integral can be done in a way that is term by term. So examples. So we have 2 more minutes, then we will finish. So let's recall we have this geometric series which is given, well known to be in this form. So if we, within the radius of convergence, and that is less than, more x less than 1, we can actually differentiate this. And then we can do the same for the right hand side, term by term. So we differentiate term by term. And so that would becomes n x n minus 1. Since n equal to 0 will vanish, so we actually start from n equal to 1. And on the left hand side, we actually have, we can differentiate this directly, don't you? So you're going to get 1 minus x squared. Excuse me, my writing. So you actually get square 1 over that. And so that is the formula holds within the same radius of convergence. So I think that is an example. So we're going to stop here and continue next time.